I'm Sean Carroll. I'm a theoretical physicist at the California Institute of Technology, and I'll be talking about some of the mysteries of modern physics. I'll say a little bit about how much physics knows, which is a lot, but the mysteries that we have left are extremely profound. So I'll talk about the nature of quantum mechanics, the nature of space, and the nature of time.
So welcome everyone to the second of the Darwin College Lectures in 2020. And as you know, our theme this year is enigmas, puzzles or riddles. Tonight, we take our instructions from Alexander Pope, the poet who called humans glory, jest, and riddle of the world. Well, after that put down calling us a riddle, he ordered us to go measure the earth, weigh air and state the tides, instruct the planets in what orbs to run, correct old time, and regulate the sun. So, following that instruction, tonight we turn to physics, once so logical and ordered. Pope declared nature and nature's laws lay hid in the night. God said, let Newton be, and all was light. But not now. As the writer J.C. Squire once wrote, it did not last. The devil shouting, ho, let Einstein be, restored the status quo. Well, where do we stand now? I think often modern physics can leave us more mystified than illuminated. And it's not just, all us non-experts. I recall a story that was circulating in my undergraduate student days here. As a student left her lecture notes in her bike basket and returned to find an old and rather ill-dressed man rifling through them, through her quantum physics notes. He said he just wanted to find out what people were being taught these days. Now, since elderly tramps don't usually read advanced maths, she gave him what for, and he apologized and shuffled off towards Free School Lane. Now, that elderly man was Paul Dirac, who, writing about a physicist's picture of nature and the differing implications of quantum physics and relativity, suggested at about that time, maybe slightly before, that the situation could be described as though God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. Dirac said he hoped advances in maths would enable better understanding of the universe. So, tonight, to discover what puzzled Dirac, what drove Einstein to the paradox about spooky action at a distance, these deepest puzzles of the quantum worlds and multiple universities, not multiple universities, there you are, multiple universes. You can tell what I normally think about. We have Professor Sean Carroll, a theoretical physicist at Caltech, who's going to speak, as you can see, on the mysteries of modern physics. So, Sean.
Thank you very much. It's, of course, an enormous honor to be here as part of the Darwin Lecture Series. I like the bottle of vodka that they have left for me here. That's also something you don't really get in the United States. But I don't know how familiar you are with the system, but when they invite you to give one of the lectures, there's a theme for the year, and they assign you a title. They're suggesting what you should talk about, roughly speaking, but then it's understood you will change the title to be what you want it to be. So this was the title I was assigned, and I did change it, but then I changed it back because I realized that rather than just give a list of my favorite mysteries or just talk about my one single favorite mystery, I would actually like to make an interesting point about the kinds of mysteries that physics is currently faced with, because we are in an interesting part of the history of physics, which is always hard to know when you're in it because you don't know what's going to happen next, but I think we can see some clues. So I will start by, this is a modern picture, of course, but I want to make an ancient point. What is physics, and how does it talk about the world? broadly construed, that's what physics is. It's the world. It's what the world is made of and how the world behaves. And the point of this picture, the point of this picture to the person who took it is no doubt the cute little dog that is driving the car right there. But to me, I want to emphasize the difference between ancient physics and modern physics. If you were Aristotle and you were thinking about physics, you had a story to tell, and that story was one of causes and purposes, right? Of natures of things to be a certain way. And from the physics point of view, one of the important points was, in order for something to move, you had to push it. There had to be a reason why it was moving. There was a natural state of being, which was for any one thing more or less at rest until you shoved it, right? So here you see that a reminder that Aristotle was no dummy. Right? In our everyday life, it is generally true that if you want to get something moving, you have to push it. And therefore, it was really quite an enormous step forward when we began to realize that that wasn't how physics worked fundamentally. There began to be a difference between sort of the underlying laws and the phenomenological experience that we have in our everyday life. Turns out to be a very long story of people realizing this. Ibn Sina, sometimes Latinized as Avicenna, was a polymath during the Islamic Golden Age. He was Persian around the year 1000. And physicists consider him extremely annoying because his day job was he was a physician. He was a doctor, and he wrote many volumes on health and medicine. And then, like, in his spare time on the weekends, he invented new fundamental laws of physics, right? This does not endear you to the community of physicists. So, as far as I can tell, Ibn Sina was the first person to say out loud that if it weren't for these messy things like friction and air resistance, what would actually happen to a moving object is it would just stay moving. That you don't need to keep something moving. Things tend to move by themselves. It's just the ordinary, or things would tend to move by themselves, but it's just that we're surrounded by dissipation and what we now call friction that prevents them. Now, it was a long time ago. Ibn Sina's point was not that that's how the world really was. He thought of this as a reductio against the idea that there could be empty space, because surely you don't think that things just move forever, right? Of course, now we know there are things very, very close to empty space. We fly spacecraft up into them, and they seem to move forever. There's no rockets propelling the Voyager probe out into interstellar space. It's just moving. And that creates an enormously different view of how the world works. For one thing, this would be a whole nother talk, but it does help naturalize our view of the world. Aristotle wrote physics, but then he wrote more than that, and he used this idea that you needed something to do the moving to prove the existence of God, right? To say there must be at some point an unmoved mover. If the universe can go by itself, that raises a different conceptual framework. Again, that's a whole nother talk. What I want to say is that this new paradigm of not causes and goals and purposes, but rather patterns. The way to think about physics, and this sort of codified in Galileo and Newton and Laplace, is if you give me the state of the universe at any moment in time, then there are equations that represent natural patterns that will tell you what happens next. And they're not they're not causing the universe to happen, they just concisely tell you what is going on. And let me show you what those laws are. First, in cartoon form, this picture basically summarizes the laws of physics underlying what I call everyday life, and I'll explain what I mean by that in a minute. But you get the cartoon image of an atom. You've seen things like that, right? There's a nucleus at the center with protons and neutrons. We now know the protons and neutrons are comprised of quarks, up quarks and down quarks. Around that spins an electron, and these different particles interact through different forces. There is the strong nuclear force keeping them together inside the proton and neutron, keeping the quarks together. There is the electromagnetic force keeping the electron on the atom. Sometimes, of course, most everything interesting you've ever encountered in your life is due to electrons moving around between atoms and in between them. And then there's, of course, the weak nuclear force, which brings to life a fourth elementary particle called the neutrino, because up and down quarks can convert into each other, spitting off neutrinos. And finally, there's gravity, pulling everything down to the Earth. Everything gets pulled toward everything else under the force of gravity. In the background of all this, as we verified just a few years ago in 2012, the Large Hadron Collider in Geneva, there is a Higgs field spread out all over the place. As I wave my hand, it's moving through the Higgs field, and that affects the properties, especially the masses of these particles. So it's a very simple picture. 4 particles, 4 forces, 1 background Higgs field. You might, if you've been hanging out on the wrong street corners and learning a little bit of physics, think, well, aren't there other particles also? Yes, there are, the strange quark and the top quark and the muon and things like that, but all of these particles decay away rather quickly. You are not made of any of those particles. These are the particles that make up you and this table and me and this laptop and really everything that you have ever seen with your eyes, touched with your fingers, smelled with your nose in your life. And furthermore, we know how they interact with each other. And even better than that, the most impressive fact is that there will not be a discovery tomorrow or next century or a million years from now which says, you know what, there was another particle or another force that we didn't know about, but now we realize plays a crucial role in our everyday life. As far as our everyday life is concerned, by which I really mean what you can see with your eyes, touch with your hands, etc., we're done finding the underlying ingredients. That is an enormous achievement in human history, one that does not get enough credit, because of course as soon as we do it, we go on to the next thing. Physics is not done. I'm not saying that physics is done, but physics has understood certain things. And those things include everything you encounter in your everyday life, unless you're a professional experimental physicist, or unless you're looking, of course, outside our everyday life at the universe and other places where we don't know what's going on. So I know that just showing you a cartoon might not be as persuasive as it could be, especially when the point is so grandiose as the laws of physics underlying everyday life are completely known. Some of you are sitting there thinking, I'm not going to believe that until I see an equation. Well, here you are. This is the equation. This is what Nobel laureate Frank Wilczek has dubbed the core theory of modern physics. It's put in a certain mathematical language. I just want to write out everything explicitly so that you're prepared for the quiz at the end of the lecture. But the point of it is, this is, remember I told you that the paradigm of physics is, if I tell you everything about the world at a moment, there's a law that tells you what the world is going to be like at the next moment, both forward and backward in time. So this is that law for the modern core theory, for the quantum field theory of all those particles I just told you about. It's a path integral that was worked out by Richard Feynman and others, and all of the stuff is in there. There's quantum mechanics, there's space-time, gravity, the other forces, so that's the weak and strong nuclear forces, and electromagnetism. There's matter, by which I mean the electrons and the neutrinos and the quarks, and there's the Higgs boson in the background. The only point of showing you this is to point out that it is a pattern. It is just a relentless thing that the universe does over and over again. It's not moving toward any goal, nor is it being pushed from outside in any way. Now, there's another subset of you that says, sure, I like equations, I'm glad you showed me that, but I only really like equations that can fit on a t-shirt. Here you go, proof that this can fit on a t-shirt. Okay. So the reason why I'm going through this, even though it's not the mystery yet, right, this is stuff we do understand, is to pinpoint this thing about the mysteries that I want to get to. We do have plenty of mysteries left in physics, but among those mysteries are not how things that make up this table, or the Earth below us, or you and me, or the planets and moon and stars behave. The mysteries are of another sort. So there's one obvious kind of mystery that, in fact, in retrospect, I really should have made a slide for, and I feel bad now, which is the collective behavior of all of these things, right? I understand how electrons behave. I understand how protons behave. I do not understand how 10 to the 25 electrons behave, especially when there are protons around. They can have all sorts of emergent properties. I will nod toward them later in the talk, but clearly that's in fact what most working physicists actually think about, and it's incredibly important. There's another set of mysteries, which is we have yet to understand what most of the universe is made of, right? And this is something that astronomers have taught us, bless their hearts. when you look out there in the sky through various ways, you realize that the kinds of particles that make up the core theory, the kinds of particles that we've detected in our laboratories and so forth, are just not enough to account for what we see. In the top left, there's the famous bullet cluster, where two galaxy clusters passed through each other. The matter heated up because it sort of ran into the matter from one cluster, ran into the matter from the other cluster. That's the red. But then you can use gravity and the lensing effect on light caused by gravity to weigh where the mass is, and it's not where the ordinary visible matter is. The blue is where we reconstruct the mass to be. So what you interpret this picture as saying, these two clusters of galaxies just went through each other, and all of the mass just went through, almost all of it. Why? Because almost all of the mass is something called dark matter, something that does not interact with the model, with the particles in the core theory that we know and love. And then we use evidence from the cosmic microwave background and from high redshift supernovae to say that most of the energy in the universe isn't even made of matter. Not just it's not ordinary matter, it's not even dark matter. The pie chart that we've constructed in the 1990s has 70% of the universe, something called dark energy, which is smoothly distributed through space and, most importantly, does not dilute away as the universe expands. There's a certain amount of energy in every cubic centimeter of space, 10 to the minus 8 ergs, if you want to know, and it remains the same even as the total number of cubic centimeters goes up. That phenomenon pushes the universe apart, and that causes an acceleration that we can detect using our telescopes. So 25% is there for the dark matter, leaving only 5% of the universe for the particles that were listed on the t-shirt right there, okay? So clearly there are mysteries in physics. No one can claim otherwise. But none of this stuff, dark matter and dark energy, it doesn't affect our everyday lives. In fact, there's a sense in which it's kind of everyday. It's kind of down to earth. I mean, after all, dark matter is matter, and we know what matter is and what it does. It's probably some particle. In fact, it's full employment for graduate students in theoretical physics to invent their own dark matter particle. You haven't worked hard enough if you haven't invented your own dark matter particle in modern physics. Likewise, the dark energy, we have a perfectly good explanation for what that could be, Einstein's cosmological constant filling all of space. We don't know the details, but it's easy to explain these phenomena in broad terms. So it's sort of normal science, in Thomas Kuhn's sense, to figure out what these things are. In addition to these kinds of mysteries, we have deeper mysteries, and that's what I want to do for the rest of the talk. I want to bring you up to speed on some of the even deeper mysteries, some of the foundational mysteries that call into question the whole paradigm that we tend to use. There's a secret way of doing physics implicit in this equation, quantum field theory, that has loopholes, has things that might not be up to the task in some way, and that's what I want to mention for you. So I'm going to have three mysteries. Mystery number one is quantum mechanics. I've already mentioned quantum mechanics. You've heard of it. How could it possibly be mysterious? Paul Dirac, whose name was already name-checked here, one of the founders of quantum mechanics, did a lot of stuff, won Nobel Prizes. We can use quantum mechanics to extraordinary precision to make predictions, to build new technologies, to understand why the table is solid, why the sun shines, etc. Nevertheless, my esteemed predecessor at Caltech, Richard Feynman, said very famously, I think I can safely say that nobody understands quantum mechanics. This statement is still true if you interpret what he meant as, I think I can safely say that nobody other than me understands quantum mechanics, not because Feynman understood it or not because I understand it, but there are people who think that they understand quantum mechanics, but they don't think that other physicists understand quantum mechanics. There's no consensus on what really is happening. And this is a long story deserving of many lectures all by itself. Quantum mechanics was sort of put into its final form circa the 1920s, the late 1920s, and there was a bit of a tussle between, on the one hand, people like Einstein and Schrödinger, who said, you know, look, so far so good, I'm impressed, but you can't say that we're done. We need to keep going. You know, but deeper understanding is required here. And on the other side, people like Niels Bohr and Werner Heisenberg and Wolfgang Pauli who said, no, we're fine. There's some mysteries in there, but we don't need to figure them out. It's good enough for government work. The motto that is put here is shut up and calculate. No one ever said that sincerely, but we accuse each other of thinking that way. So this is what Feynman means. It's not that we can't use quantum mechanics, but when you ask what is really going on, and I'll explain what I mean in a second, we can't give you a significantly consensus answer. And that's okay. Not understanding things, having mysteries is great. That's how you make progress, trying to resolve the mysteries. What's not okay is that we're not trying. That the field of physics over the last 90 years has largely abandoned the project of trying to understand what goes on in quantum mechanics. I analogize it to this famous fable, Aesop's fable, the fox and the grapes. Do you know this one? The fox was walking around and he sees this bunch of grapes up on the vine, and the fox says, I want these grapes. He jumps to get them. They're just out of his reach. He cannot get the grapes. So after a few tries, the fox says, you know what? I never wanted those grapes anyway. They were probably sour. You're not supposed to explain your parables, but just so it's clear, the fox represents physicists. The grapes represent understanding quantum mechanics. We used to admit that we wanted that, and now we're like, no, we don't even want to understand quantum mechanics. What's up with that? Let me give you a very brief reminder of why quantum mechanics came to be and what it says. So here's another Cambridge icon, right? The Rutherford atom. This is something I already showed you, but we're just going to boil it down to its essentials. Nucleus in the center, electrons orbiting around it as if they're planets in a solar system, right? So, sorry, Cambridge, but I have to say, this is nonsense, this picture. We know this picture is not right. They knew it very, very quickly after they invented it. Why? Because another famous Canterbridgian, Isaac Newton, came up with this thing called classical mechanics. That was the predecessor to quantum mechanics, and classical mechanics is pretty straightforward about what happens when particles and forces move around. In the 19th century, we put together this theory of electromagnetism, Faraday and Maxwell and their friends, and it said the following thing. If you have a charged particle like an electron, there's an electric field pointing toward it. So if I move the electric field adjusts to point to the new position. So if I move the electron up and down, the electric field responds by waving, and those ripples move out at the speed of light because they are light. That's what light is. All the light in this room is made by electrons waving up and down, giving off electromagnetic waves. That's how light works. These electrons should be giving off light. They're spinning all around, right? This counts, orbiting like that, counts as being shaken up and down. So classical mechanics, together with the specific equations of classical electromagnetism, predict that the electrons should be losing energy and therefore spiraling in to the center of the nucleus. They should not remain on constant orbits. You can even ask how quickly it should happen, and the answer is about 10 to the minus 11 seconds. About 1/100th of a billionth of a second. So I'm a theoretical physicist myself, but it's always good to do experiments to see what happens. So let's do this one. It didn't happen. This table, you, me, the Earth, should all collapse to a point in a tiny, tiny fraction of a second if classical mechanics were true. Now, normally, when you come up with an anomaly like this, the physicist's first move is to be conservative, right? Can we just change the rules a little bit to save the phenomenon? But eventually, if you try very hard, you're led to something completely dramatic and paradigm changing. That's what happened in the case of the atom. The idea that people came up with was electrons are not particles. Despite the picture, that they look very particle-like, really the electron is spread out in a sort of a cloud that we cleverly called the wave function. It's not really very clever. It's the most boring name in the world for the most interesting and important concept in the world. The electron is stable with a certain size around the nucleus because it's kind of like taking a string that is attached at both ends and plucking it. There's going to be a lowest frequency it can vibrate at, and there's going to be harmonics that will come in a discrete set. Likewise, the various shapes of the electron's wave function sitting in the vicinity of an atomic nucleus come in a discrete set. There is a lowest energy place the electron can be, and it's not a point-like thing at the center of the nucleus. It's a little cloud that is spread out over a certain size. And then there's a rule that two electrons can't be doing exactly the same thing, so if you put more and more electrons around the nucleus, they get more and more Baroque shapes. Any of you who've taken chemistry classes have been tortured by pictures like this, orbitals, right? You've heard of these words, okay?
So this is a wonderful idea. It explains why atoms don't decay. It even explains why certain kinds of radiation from atoms come in discrete, predictable frequencies, because you're jumping from one of these sort of energy states to another one. Best of all, there is an equation. I love the equations here. This is the Schrödinger equation, okay? I'm not going to go into the details of explaining this one any more than the last one, but the point is this wave function for the electron, the Greek letter psi, obeys an equation, which means that we're back in the good old paradigm of physics, where I tell you what the thing is doing right now. This equation is what tells you what happens in the future. It's once again one of these patterns that is obeyed by nature. For a physicist, having an equation like this is just the happiest place they can be, because they can assign problems to their students, solving the Schrödinger equation in all sorts of different situations. This is an enormous triumph at a great cost, because you changed quite dramatically what you meant. You thought the electron was a particle, now you're saying it's a wave. There's a problem when you look at the electron, which is that it doesn't look like a wave. So you can use the Schrödinger equation to make predictions like when a radioactive substance emits a particle, how does that particle move away from the substance it was emitted by, like a nucleus decaying and spitting out an electron? The answer is it looks very much like one of these shapes. It will sort of spread out in a more or less spherical configuration, a big puffy cloud. They'll move out in all directions and get essentially attenuated over time. Then when you look, this is what you see. This is an actual uranium sample in a cloud chamber, which means that when a particle moves by, a charged particle will take off some electrons from the atoms nearby, and you will see that as a little bit of a cloud. And what you see very clearly is not one big puffy thing, but a set of individual trajectories, as if a particle has been emitted from the substance and is moving away from it when the radioactivity occurs. This is really hard to wrap our heads around if we already said that electrons are not particles, they're waves. It's almost as if the electrons are waves when we're not looking at them and particles when we look at them. So the greatest minds in the history of physics got together and thought about what's going on, and they came up with the following paradigm. Electrons are waves when you're not looking at them, and they're particles when you're looking at them. What can I tell you? This is still what we teach our students. This is called the Copenhagen interpretation, or the textbook interpretation of quantum mechanics. It says that on the left, you might have some spread out wave function for an electron sitting there all by itself, but when you measure it, when you take a picture of it, when you say, where is it, it suddenly collapses to a point, and it looks like a particle. And furthermore, you can't even tell me where it's going to collapse to. The best you can do is calculate the probability that it will collapse to different locations, and the probability is governed by the wave function. When the wave function is higher, there's more probability. When the wave function is very small, there's less probability. So I am not making this up. When we teach quantum mechanics to our students, whether it's Cambridge or Caltech or anywhere else, there are two different sets of rules that come along with quantum mechanics. There's one set of rules for how quantum systems act when nobody is looking at them. And those rules are very down-to-earth and sensible. There's quantum states, which take the form of wave functions, and they have an equation, the Schrödinger equation. It's very much in the classical paradigm. And then when you look at them, when you measure them, when you observe them, all hell breaks loose. You can't predict exactly what's going to happen. There's just a probability, and the wave function changes suddenly and discontinuously. This is what we teach our students. And the problem with this is that it's clearly nonsense. This is clearly unacceptable as a fundamental theory of nature. So here are two problems. One is the measurement problem, which is just, if you look back at these rules, what in the world do you mean by when somebody looks at it? What counts as a measurement? Does it have to be a human being? I mean, could a cat count as looking at something? What about a video camera? Would that count? What if I just glance at it at the corner of my eye? How quickly does it happen? Why is it probabilistic, et cetera? So none of these questions is answered by the conventional Copenhagen interpretation. This is why people like Einstein and Schrödinger, they didn't say quantum mechanics is wrong. They said that's a good sort of halfway put together idea. We need to do better. We need a more mechanistic underlying model. And the other one I want to emphasize is the reality problem, right? I mean, I said quite explicitly, because I think it's true, the electron is a wave function, right? That's what it is, not a particle. But is that exactly right? There are other people who will say, well, reality is partly wave function, but there's other things going on also. Maybe the reason why electrons act like waves sometimes and particles other times is because they're both. They're both waves and particles. Or maybe the wave function is just the tool that we use to calculate probabilities and has no reflection of reality whatsoever. The fact that we don't know 90 years after we put this theory together is an enormous embarrassment to physics. And if you tried to know, if you were a student in the back of the room who raised your hand and said, like, I don't like this thing you're telling me, I would like to try to do better, we gently nudge you out of the field, physically, or you go willingly or not. This did not stop people from trying. So here's my favorite version of how to solve these problems. Hugh Everett was a graduate student in the 1950s. He worked with John Wheeler, who in turn worked with Niels Bohr, so he was in the tradition of the great people of quantum mechanics. And if anything, Everett's approach was just as much therapeutic as it was scientific. Basically what he's saying is, guys, you're working too hard. You don't need to bend over backwards with all these crazy rules just to understand what we see in experiments. You want to know what's reality? It's the wave function. It is precisely represented by the wave function. There's nothing extra there. You want to know how the wave function behaves? It obeys the Schrödinger equation. You know that it obeys the Schrödinger equation sometimes. I claim it obeys the Schrödinger equation all the time. That's all that ever happens. So he says, relax. Of course, we know that there's a problem with this. But let me just emphasize how simple the idea would be if it worked. Here's Everett's version of quantum mechanics. There's not two separate kinds of rules. There's just one set of rules, and it's just there are quantum systems described by wave functions, and they obey the Schrödinger equation, and that's the end of it. How much simpler the lives of students would be when we taught them quantum mechanics if that's all there were to it. The problem, of course, is this issue I mentioned, that when we look, we don't seem to see wave functions. We seem to see particles. So how in the world can we reconcile this very beautiful, pure, austere, rigorous framework with the evidence of our eyeballs when we actually look? So that's a little subtle, but it's worth explaining. So I will conjure up the thought experiment stylings of Erwin Schrödinger, who famously put a cat halfway to death inside a box. So Schrödinger's cat is inside a big box. There is a quantum event going on, like a radioactive source, which is detected by a detector. And if the detector fires, it lifts open a little container and releases gas throughout the box. In Schrödinger's way of doing things, the gas was cyanide. And if the gas was released, the cat died. Killing the cat does not increase the physics understanding in any way whatsoever. So in my version, it's just sleeping gas. And when it's released, the cat goes to sleep, but there's still a little smile on the cat's face, okay? No harm is done to any cats in these thought experiments. The point of Schrödinger's thought experiment, which was developed in correspondence with Einstein, because they were on the same side in this debate, is not to say, wow, look how cool quantum mechanics is. It's to say, surely you don't believe that. Because if you believe the rules of quantum mechanics, it's not that the radioactive source either decays or doesn't. It's that it has a wave function, which is a superposition of I have decayed and I have not decayed. Just like the electron does not have a definite position, it's a wave function spread out over all the different possibilities, the quantum state of the radioactive source is not one or the other, it's a superposition. And when it comes to tiny microscopic things, like a radioactive nucleus, we think that's okay. Schrödinger's thought experiment is meant to amplify that quantum weirdness to the macroscopic level. So if you believe the Copenhagen interpretation that wave functions obey the Schrödinger equation until you look at them, and you don't count the cat as an observer, then what happens is the detector goes into a superposition of I've detected a decay and I haven't. The container goes into a superposition of I have opened up and I haven't. And the cat goes into a superposition of I am awake and I am asleep. So that's the real oomph of Schrödinger's cat. It's not that we don't know. It's not that there's a cat in the box that is either awake or asleep and we're just ignorant of the truth. It's that there's a prediction of quantum mechanics that there is a cat inside the box that is in a superposition of both awake and asleep. And the story the Copenhagen interpretation would tell about this is to say, here's the cat, superposition of awake and asleep, but the observer, in square brackets, is classical. So I'm putting quantum things in parentheses, classical things in square brackets. Here, the role of the observer is played by Niels Bohr. And the story that you're told is when you open the box, there's a collapse of the wave function. You never see the cat in a superposition of awake and asleep. You either, with some probability, see the cat awake and the cat is awake, or you saw the cat asleep and you see the cat asleep. And that's what the cat was doing. Here is Everett's version of exactly that same story. Remember, there's no collapse of the wave function, but also there's no classical world. You don't treat, in Everett's formulation, human beings any differently than you treat electrons. They also have a quantum mechanical state. And Everett makes use of a crucial feature of quantum mechanics that was highlighted by Einstein and collaborators in the 1930s called entanglement. This is a longer story, but in quantum mechanics, different subsystems of the universe do not have their own wave functions. There is only one wave function for the whole universe. Everett cleverly called it the universal wave function. Stephen Hawking called it the wave function of the universe. It's the same idea. Everything belongs to the same wave function, and therefore, you can't isolate the quantum state of one thing, the quantum state of something else, the quantum state of a third thing. You have to talk about all of the universe at one time. That enables this thing called entanglement, where the observable features of one subsystem of the universe might be related to the observable features of another one in a way that would be impossible in classical mechanics. So here's the Everett version of Schrödinger's cat. You start with the cat and the observer. Here's the cat in a superposition. The observer, now played by Hugh Everett, is treated quantum mechanically. Therefore, parentheses. And measurement is nothing spooky anymore. Remember, Everett just says you just evolve everything according to the Schrödinger equation. There's no separate kind of evolution. And here's the interesting point. Everyone agrees, no matter what you feel about quantum mechanics, everyone agrees that if you just take the observer and the cat and treat them using the rules of quantum mechanics, we know what they're going to evolve into. What they will evolve into is a superposition of an entangled state where part of it has the cat awake and the observer saw it awake, and part of it has the cat asleep and they saw it asleep. Everyone agrees on that part. The question is, what are you going to do about that? And the question comes up because you would think that if that happened to you, you would feel like I've kind of both seen the cat awake and seen the cat asleep. But I've never felt that way. No one has ever felt that way, therefore this can't be right. What Everett's genius was is to say that both of these parts of the wave function exist and are real, but they go their own separate ways. This part of the wave function will never interfere or otherwise affect that part of the wave function. And there's math involved with this, and you can argue for it, et cetera. But the point is, these two parts of the wave function, once that entanglement happens, behave as if they are separate worlds. So you can just point at, you can say, the me that is doing the experience of looking at the cat is not the combination of both of these things. It's that there was one me and now there are two me's. There is a me that saw the cat awake and a me that saw the cat asleep. So as time goes on, the universe has a wave function that branches into more and more separate worlds. This is why a good PR man, in this case Bryce DeWitt, relabeled the Everettian quantum mechanics theory as the many worlds interpretation of quantum mechanics. But what I want to emphasize is at no point does Everett or DeWitt or anyone else put in a bunch of extra worlds. The worlds were always there. All Everett ever did was remove things, namely some clunky, unjustified extra rules about what happens to quantum systems when you observe them. If you believe that an electron can truly be in a superposition of here and there, then you should believe that a cat can truly be in a superposition of awake and asleep, and therefore you should truly believe that you can be in a superposition of having observed the awake cat and having observed the asleep cat, and the universe can be in a superposition of those two things, and then it's just math to show that those two parts of the superposition have a life of their own, no longer affect each other, are separate worlds. That's not to say this is true. If I had, you know, a 10-lecture series rather than just this one, we could mention all the alternatives to this. There are some very, very bright people in this room who don't quite believe this picture, no matter how compelling and obviously correct it is. But the lesson that I want to drive home is not that many worlds is right. It's not that Everett is right. That's true, but that's not the lesson that I'm trying to get at. The lesson I'm trying to get at is that it matters. I mean, sure, what the dark matter and dark energy are perfectly good mysteries. But this is a prior mystery. This is a mystery that's been around for longer than that. And it's a deeper mystery. It's not about, like, identifying some substance. It's the basic rules by which nature operates. We should not abandon the project of trying to figure this out. Feynman may be right that we don't understand quantum mechanics, but we shouldn't be proud of it. We should be embarrassed and move forward. Which brings us to mystery number 2, which will be related. Mystery number 2 is how gravity and space-time come to be. So again, this is a situation where there are non-mysterious things. This young man, Albert Einstein, everyone shows you a picture of when he was not a young man, right? But when he was young, someone was combing his hair. He was a sharp-dressed guy. He was not wearing the rumply sweaters, and he was inventing theories that changed how we thought about the universe. Special relativity came along in 1905. That's the theory where space and time are both part of four-dimensional space-time. The speed of light is an absolute limit, and so forth. General relativity comes along 10 years later. That's the theory that says space-time has a life of its own. It is curved, it is warped, it is dynamical, and you and I feel that warping as the force of gravity. Einstein says the reason the laser pointer falls down is because the Earth has energy. That energy bends the space-time around it, and all the laser pointer is trying to do is describe a straight as possible line in this curved space-time background. This theory, as I'm sure you know, has been extraordinarily successful. Arthur Eddington, another Cambridge guy, showed that space-time, the prediction that Einstein made, that space-time can deflect light, can be experimentally tested. Recently, we tested it to much higher precision by looking at gravitational waves emitted by in-spiraling black holes. That's the good news. The good news is this wonderfully amazing theory. And, you know, I feel bad zooming over it so quickly. Einstein wrote down some equations in 1915. And implicit in those equations, even though he didn't know it at the time, were the ideas of black holes and in-spiraling and gravitational waves and gravitational wave detectors. And in 2016, 100 years later, we actually detected it. Like the power of the combination of the human imagination and nature's stubborn insistence on obeying the laws of physics enables something scribbled down in a notebook in 1915 to show up in a billion-dollar experiment 100 years later, which I will never get tired of being amazed at. The bad news is, I just told you about quantum mechanics. Einstein's theory is resolutely classical. It says that there is something called space-time. I can tell you how it evolves. You can measure it, etc. There are no wave functions, no entanglement, nothing like that. But in some sense, in a very clear sense, quantum mechanics is more fundamental than general relativity is. General relativity is in the classical paradigm. Quantum mechanics throws away the classical paradigm. How are we going to get them together? People have tried to do this without that much success so far. So what I want to suggest is there's a way forward, but first just remember this motto. General relativity boiled down to 2 words, geometry, energy. The geometry of space-time is influenced and influences, in turn, the energy within it. So here's my suggestion. Even though physicists trained on quantum mechanics are very smart cookies and know a lot about what they're doing, they still grow up thinking classically. There are no babies. There is a book, Quantum Physics for Babies, but I don't think it really works. I don't think the babies really think in terms of wave functions, that Schrödinger equation. Most of us have a classical intuition, and because of that, when we try to invent quantum theories for new phenomena, we traditionally start with classical theories and quantize them. This, I think, has the potential for holding us back, because nature doesn't do that. Nature doesn't start with a classical theory and quantize it. Nature is just quantum from the start. So maybe it will work sometimes, and indeed, that picture I showed you with the big equation of the core theory is a series of success stories where you start with classical versions of electromagnetism and quarks and so forth, and then you quantize it. But when it comes to gravity, that seems to have failed us. If you quantize general relativity in the straightforward way, it does not work. And what I want to suggest, and other approaches like string theory, are essentially proposing different classical theories that you then go quantize. What I want to suggest is that maybe we should take nature seriously, take quantum mechanics seriously, and rather than trying to quantize gravity, to try to find gravity within quantum mechanics. Not to start with curved spacetime, but to start with wave functions and entanglement, and ask if we can point to curved spacetime emerging out of those quantum notions. So we're allowed to cheat when we play this game, okay? We're going to cheat by using things that we know about the world from where physics does work. Forget about gravity, think about quantum field theory, like the core theory I showed you. This is another wonderful feature of modern physics, that the world is really not made of particles, it's made of fields. So you know about the magnetic field, here's the magnetic field in action around a magnet, but in fact, the electrons and protons that make up stuff, that make up matter, are also vibrations in quantum fields. The real stuff of the world, according to quantum field theory, are these fields that pervade all of space, and where you think that there isn't anything, where you say, oh, there's no particles or forces or anything here, it's just that the quantum fields are there, but they're what we call in their vacuum state. They have the least amount of energy it is possible to have. This point of view changes what we mean and how we think about empty space. So if you were in a particle view of nature, you would think that there are particles and there's some distance between them, but in between there was just space. That's all there was. And space was the same at every place. But if you think of the quantum field view, a particle is just a field that's vibrating a little bit more than it wants to, and all of the other regions of space also have quantum fields in them. So they're both fields, so they're there, and they're quantum, so they can be entangled. So different parts of empty space have a very interesting, complicated quantum structure. There are particle physicists whose life is devoted to understanding the vacuum, to understanding empty space. Most physicists want to have at least a particle or two in space before they analyze it, but there's a lot of richness just there in empty space. And there's a feature of this entanglement. So if you look at nearby regions of empty space, so here I've removed all the particles, space is just empty, but I isolate a region, another region nearby, and there are quantum fields vibrating in those regions, and guess what? I can calculate the entanglement between them. And the answer is, if the regions are nearby, they're highly entangled. If the regions are far away, they're not very entangled at all. So when I'm in this context where I have space and geometry and so forth, there's a relationship between geometry of space and entanglement. What I want to suggest is we can reverse that relationship. When I mentioned that relationship, I was talking the language that space already existed, but if we want to see whether space can emerge from quantum mechanics, all of our initial vocabulary should be words like wave functions, entanglement, and so forth. So instead of saying when two regions are nearby, they are highly entangled, let's say when two quantum degrees of freedom are highly entangled, they are nearby. That is what we mean by nearby. Nearby is just a colorful way of talking about the amount of entanglement between abstract quantum degrees of freedom. So if you give me a whole collection of abstract quantum degrees of freedom and the amount of entanglement between them, there can be an emergent geometry. Here's a three-dimensional geometry, here's Euclidean geometry, here's a sphere, depending on the quantum state of the system you're looking at. Keep that in mind. And I will also mention something a bit more subtle, that there's a relationship between entanglement and energy. Remember, when we had just empty space, I could tell you how entangled different things were. Now let me start putting particles there. Let me add energy to a region of space by putting particles in it. But putting a particle in it in this language is actually just making the field vibrate more there. And what that does is it breaks the entanglement between that region and the regions around it. So when you put particles and therefore energy in a region of space, the entanglement between that region and the regions around it goes down. So I want to play exactly the same game. Let me go the other way around. When I have a collection of quantum degrees of freedom, if I lower the entanglement, I interpret that as putting energy into that region, therefore giving me a relationship between entanglement and energy. So what I have, I know this is very fast, but you're going to trust me. What I have then is by using entanglement, I can relate it to geometry. I can also relate it to energy. And therefore, by the rules of arrows, I can relate geometry and energy to each other. But of course, that's exactly what Einstein did. And in fact, when you attach the equations to this story I'm telling you, you can derive, in some very, very limited contexts, Einstein's equation for general relativity from purely quantum mechanical starting points. In other words, we don't know because there's a very long, complicated program ahead of us, but we've just started this very ambitious program of starting with pure quantum mechanics and seeing whether or not we can get curved space-time and general relativity to emerge from it, rather than quantizing a classical theory. So this is still a mystery right now, but this might be a mystery we can really make progress on by taking quantum mechanics seriously. Final mystery, this is more or less understanding space. Why don't we try to understand time also, right? My favorite part of time is the arrow of time. The arrow of time is just the fact that the past and the future are different in important ways. So if I showed you these pictures of these young lads and said which was the younger picture and which was the older picture, you would all know certain things happen to us as we age, right? Certain things happen to society as it passes by. When I give this talk in the United States, that's Elvis that I show up there. And this is the signing of the Declaration of Independence, but I thought that'd be bad form to show here. So Magna Carta is what's representing the past, okay? This, of course, everyone knows what this is, I presume. This is from Charles Darwin's notebook. This is the first appearance of the tree of life going up. So he didn't put an arrow saying time goes this way, but it does. This is him saying from one species you can evolve into many different species. That's usually how it works, the arrow of time at work. The best thing, the reason why everyone loves this picture, of course, is he says, I think. At the top, that's a warning to the rest of us. You know, don't be too confident. Why is the past different from the future? That's not exactly the mystery that I want to highlight. I think we mostly know why the past is different from the future, and the answer is something called entropy. Entropy is a way of characterizing how disorderly, random, disorganized, messy a physical system is. And there's a law of nature, the second law of thermodynamics, that if you leave a system to its own devices, if you don't clean it up, fix it up, organize it, entropy will increase over time. It's very natural. This is a terrible, terrible illustration that I chose because clearly putting it in a frying pan is not a closed system. But the point is that it's easy to turn an unbroken egg into scrambled eggs. It's very hard to go backward. Same thing is true in your rooms here at college. You might notice that they tend to get messier left to their own devices. They do not spontaneously clean themselves up. Law of nature behind that. And this is a mystery, this law of nature. It was a mystery 150 years ago because the underlying laws, Newton's laws or that equation I showed you for the core theory, don't have any difference between past and future built into them. And yet, the evolution of entropy does have a difference. It goes up as we go from the past to the future. What's going on? Long story short, the arrow of time has the same kind of origin as the arrow of space. What do I mean by that? If you're up in your astronaut suit in orbit, there's no arrow of space. All the different directions if you're floating in your astronaut suit are the same. Up, down, left, right, forward, backward. But here on Earth, there's clearly an arrow of space. When I dropped the laser pointer, everyone knew it was going to go down, right? There's a difference between down and up here on Earth. That's an arrow. But you also are not under the impression that the reason why the laser pointer falls down is that, as Aristotle might have thought, there's something fundamentally different about up and down. We know it's a local contingent fact because we live in the vicinity of a very influential object, the Earth. If we were up in the astronaut suit, that arrow would not exist. Likewise, what I'm suggesting here is that the arrow of time has the same feature. It's not embedded into the laws of physics. It's a reflection of the fact that we live in the aftermath of a very influential event, something you may have heard of called the Big Bang. 14 billion years ago, the universe was very, very orderly, okay? It was very, very low entropy. Nobody knows why. That's a true mystery. That's a mystery worth writing books about and things like that. Again, people in this room have done this. We think that if you start with a low entropy past, Boltzmann and Maxwell and Gibbs and others explained why entropy will tend to increase. What we do not know is why it was so low in the past. So the general fact that entropy increases, I think, is the correct explanation for the arrow of time, but there's still two very profound mysteries attached to it. One is, why did it start off so small? This is clearly a job for cosmologists, for physicists, maybe theologians, if you're oriented that way. The other mystery is, how exactly does entropy account for all of these other asymmetries of time? Why did the Beatles look different in 1963 and 1969? Is you really going to tell me that's because of entropy? Yes. Yes, I am going to tell you that. So there's a lot of work to be done here. This is why it's one of the mysteries. Let me give you enough of an argument that you can think it's reasonable. Why do you remember the past but not the future, right? Why do you have photographs of the past but not the future? This is a joke, Mitch Hedberg joke. He says, why are my friends always showing me pictures of themselves saying, this is what I looked like when I was younger? Don't all pictures show us what we looked like when we were younger, right? We don't have records or photographs of the future. Why not? So here's a record. Here's an egg. This is what we use, egg and cream and coffee. These are the only allowed options to illustrate entropy increase. You come across an egg lying on the sidewalk, broken. You say, what does the future of the egg hold? Maybe somebody will clean it up. Maybe a dog will come by. Maybe a rainstorm will wash it away. There's many possible futures of the egg. What did the past of the egg probably hold? Most people would say, I bet there used to be an unbroken egg and somebody dropped it. So somehow, just with that little piece of information, we have much more leverage on saying what the past of the egg was than we do on the future of the egg. Why is that? It's not because of the fundamental laws of physics. The fundamental laws of physics, given what you know, there's a broken egg, predict a number of possible futures and an exactly equal number of possible pasts. The difference is we also have this belief, called the past hypothesis, that the universe started near the Big Bang in a low entropy state. So adding that gives you an asymmetry between past and future. There's no future hypothesis. There's no future low entropy state, at least not in the near future. So knowing both the current state and the fact that it came from low entropy allows us to reconstruct that the most likely way to get a broken egg is to get an unbroken egg and break it. So this is a paradigm. This is a way of getting at the many different ways that the past and future are different from each other. Add in the fact that entropy is increasing from a low entropy past, and then argue about the macroscopic, visible, phenomenological, everyday world. That's where the arrow of time is so vividly observable. But there's a lot of work remaining to be done. There's no equations in this picture, okay? There are many ways in which the past is different from the future, not just memory, not just aging, but again, biological evolution. What about cause and effect? If I swing my arm and I knock the glass off the table, you're very naturally going to say something like, the glass fell because I swung my arm. No one is ever tempted to say, I swung my arm because the glass was going to fall. There's a temporal asymmetry here. I think it's because of entropy, but I haven't actually proven that mathematically yet. I'm literally working on a paper about that. I think it's provable. But this is an incredibly rich area to think about for all the young physicists or proto-physicists out there. The fact that entropy is increasing is enormously important literally to our existence. Here's a picture by a famous artist named Roger Penrose, who's also dabbled in mathematics and physics. The point of this picture is when you think about the sun is a bright orange thing that we see in California that you may never have seen here in the UK. But what do we get from the sun? Well, you might say we get energy from the sun. True, but it's not quite the point. The Earth, modulo global warming, the Earth radiates back into the universe just as much energy as it gets from the sun. The difference is, for every one photon of light that we receive from the sun, we radiate away 20 photons back to the universe. We get visible light from the sun, and we radiate infrared light back to the universe with, on average, 1/20th of the energy each. Again, go through the math. What that means is we have increased the entropy of that energy we get from the sun by a factor of 20. The reason why life is possible is because the sun is a hot spot in a cold sky, reflecting the fact that we live a very, very far from equilibrium existence. If the sun was not there, and the whole sky was the temperature of the night sky, we would all freeze and life would cease. But if the whole sky was the temperature of the sun, we would get a lot more energy, and we would all burn and all life would cease. What keeps us going, what keeps the fish rolling around in the fishbowl, is the fact that there's all this low entropy energy which we can then use to live and give back to the universe in a highly degraded form. More stuff we would like to understand better. We have a sketch in our brain of what's going on, but nowhere near a full quantitative understanding. Finally, sometimes people say when they see things like cows and people and fish and colleges and countries, they say, you know, all this looks very organized to me. Some countries more organized than others. We can bond over the lack of sensible organization in our countries of late. But where did that come from if the natural law of nature is for entropy and disorder just to increase? How in the world does increase of disorder lead to such exquisitely ordered things like people and societies? So the answer, again, we don't know the full answer, but we have the hint. The hint is entropy can increase. Here's cream and coffee going from low entropy to high entropy, all separated low entropy, all mixed high entropy. But you notice that this is very simple. All the cream's on the top, all the coffee's on the bottom. This is also very simple. They're all mixed together. It's in between, when the cream and coffee are just beginning to mix together, where it's a medium entropy state. That's when things look complicated. That's when there are swirls and tendrils and fractal patterns inside what's going on. Literally, if you took a photograph of this and put it on your computer, this image and this image would take up less bytes on your computer than this one, because there's more information there to be stored in the image. That seems to be not an absolute rule, but a very common feature in the universe. Entropy just goes up, but complexity first goes up and then goes away as you approach equilibrium. So the point is, it's not despite the fact that entropy is increasing that we can get orderly things like you and me. It's because of the fact that entropy is increasing. If entropy were not increasing, we would not be able to use this resource that we have to live and think and do interesting things. And this idea that complexity first comes and then goes is not just cups of coffee. The universe shows exactly the same behavior. At very early times, it was very, very simple and low entropy. At late times, it will be very, very simple again and high entropy. It's in between. It's right now, cosmically speaking, that the universe is at its most complex and most interesting. We live in the fun, Friday night, let's go crazy part of the history of the universe, something to be grateful for. So just to conclude, my very last slide is there are so many ways in which these mysteries could possibly be resolved, yet remain to be resolved. I'm trying to highlight that there's sort of the famous mysteries that everybody talks about. What I've tried to do in the talk is to highlight some of the lesser known, but in some sense more profound mysteries that we have. And I'm very much of the belief that concentrating on these deep mysteries opens the possibility to understand a whole bunch of things. There's, quantum gravity, of course. Here's a black hole, artist's conception. This much less interesting picture is an attempt to apply quantum mechanics to the universe as a whole, to think of the whole universe as a quantum computer in some sense. In a very different vein, this is a potential beginning place for life itself. Life is not something that is anti-entropic. Life is something that uses increasing entropy to come into existence. Filling in the details will take time. And then once life starts, how life works is something which also relies on increasing entropy. We have some crazy ideas, me and others, about why the early universe had low entropy that might take us back to the starting point, trying to understand quantum mechanics and the emergence of space-time. So I think that, the lesson is mysteries are the good part of science, right? Mysteries exist on all levels of complexity and solvability. Physics is nice enough to be in a situation where some questions have been answered, and yet the ones we are still facing are very, very deep indeed. Thank you very much. Thank you.
Thank you very much indeed, Sean. Thank you for taking us from, this guided journey from everyday core physics, which seemed pretty straightforward the way you put it, to the mysteries of quantum entanglement, many worlds, space-time and gravity, time, entropy, and so on. I mean, in some ways, for all of us non-physicists, it's really quite encouraging that even physicists have no common understanding of these hard matters. And I just note that Max Planck once commented that science cannot solve the ultimate mystery of nature. I wonder, and I'm sure it's a question for hours and hours of discussion later tonight, could there be someday a common understanding? How far can we get in these mysteries? So, next week, we move back in time to ancient Greek technology and astronomy, when Dr. Joe Marchant, journalist and author, is going to lecture on decoding the heavens, the Antikythera mechanism, and we hope to see you there then, you here then, rather. But so finally, Sean, thank you very much indeed for coming to Cambridge to talk to us this evening for a fascinating lecture. Thank you.